I'm glad to present our first mini-course lecture, Eitan Sayag from Congruent University. He will teach us representations of p-adic groups.
Thank you very much. It's a pleasure, and thank you very much again. It's a pleasure and an honor to speak here. Of course, it's quite impossible for me to teach you a representation theory of p-adic groups or of anything, but I will try to present some aspects of representation theory of p-adic groups especially. And I hope that with other courses that are going to be presented here, you will see similarities as well as differences between these realms. So I assume that with the audience present, I do not have to give a lot of motivation why one would want to study representations of p-adic groups. Nevertheless, it is quite important to have on the blackboard an item like that. So the first item would be motivation. And because as we well know, I mean, we have to justify everything we do. So the main motivation is that it's cool. So the point is that if you are an algebraist, you can enjoy it. If you're an analyst, you have your spot there. If you're a geometer, you have a heads up. So all these languages are available when one thinks about representations of p-adic groups, and in a quite mysterious way, I would say. So on one hand, the study of the category of smooth representations, which will be the main purpose of this course, is something which has this algebraic aspect. On the other hand, there are some analytic questions regarding the growth of matrix coefficients, and they are very similar to things which people in real groups are familiar with. And this some kind of an analytic aspect which we will not touch at all, but we will feel it in some sense when we are going to discuss the notion of cuspidal representations. And as I mentioned, there is also a geometric aspect. One can view those representations in the language of sheaves. Again, an aspect I will only touch little upon. So this is the first motivation. And the second motivation is that these representations naturally occur in number theory. So recently I was asked why representation theory is interesting, and I was told that yes, we heard that vector spaces are important, it's in quantum mechanics. And I said, of course, representation theory is also in quantum mechanics. But I cannot say that about representations of p-adic groups. On the other hand, we can honestly say that when one studies automorphic forms or just modular functions, then there are some aspects of this study which are encoded in the representations of p-adic groups. Okay, so this is the motivation. I pay very little to discuss that, and I hope that with this audience it's not needed. In other audience, I would probably invest half an hour in giving some. Okay, so what is the purpose? So the title is Representations of p-adic groups. And again, this is a huge domain, and I will certainly not be able to cover the many aspects of it. So within this title, I will try to discuss. So this is motivation, goals of these lectures. So there would be, the main goal would be to present to you the main definitions, the main objects which play a role in this theory, and to present some glimpse of the facts, the theorems, and some ideas how these theorems are proven. So I would want to introduce p-adic groups. Again, I assume most of you are familiar with that, but I will talk about p-adic groups. Or a p-adic group, I will associate, I will say more about what G is. I will associate two, let's call it mathematical objects. The first one is a category, an abelian category, so long to all analysts. And a set, which I will denote by G, which will consist of the set of irreducible objects, the set of irreducible representations of the group G. And maybe the main goal of these lectures would be, first of all, that any one of you would have at least 3 groups in his head. Just he or she will be able to describe a group and to say something of substance about the definition of this category and its structure. So in short, I want to describe Bernstein's theory of decomposition of this category. And in particular, this theory allows a decomposition of the category into a product of other categories. So this is completely algebra, yes? You have a category which you don't know where it comes from, and lo and behold, it's a product of other categories we don't know anything about. But in fact, we will not just talk about categories. We will really talk about objects, and I would want to give some description of the set of irreducible representations. And one of the miracles, I would say, or the magics of this story, is that the set of irreducible representations, shocking as it may be, is an algebraic variety. Well, it's not CP2. It is a little bit less elementary than that, but on the other hand, from some perspective, it's not that bad. And this algebraic structure allows better understanding of the category. Okay, so these are the, grosso modo, really the big goals, but I have kind of an itemized list of notions I would want us to discuss. The main notion, I would say, is the notion of a cuspidal representation and its various occurrences in this theory. And I will try also to give some examples for these objects, for these representations. Okay, so this is kind of the big layout. I will be more concrete about theorems I would want to discuss. So let's kind of start from the beginning. So in the beginning, there was Q, and we embedded into R. But then some bad guy said, well, you can also embed it into other fields, QP. Okay, so I assume that you're familiar with this field, okay? Field of p-adic, the field of p-adic numbers. And as I said, from number theory, people were interested in representations. So there is a certain amount of interest in representations of the following group. It's a very concrete group. So the p-adic numbers are obtained from a certain completion of the rational numbers with respect to a certain metric. I think I shouldn't write it. But in particular, we can consider representations of the following group, G, which is GL2 of the p-adic numbers. Is this visible, by the way? OK. So so I have not defined this group. So let's define the group. It's the set of 2 by 2 invertible matrices whose entries belong to the field QP. OK? So this is just a group. And I have not defined what representation is, but I will give more general setup to that in a second. And it would be of interest, or it was of interest, to make a list of the representations of this group. OK? So the basic question which people in representation theory ask without offending anyone is make a list. So of course, it's unreasonable to make a list of just representations. So you invoke or introduce the notion of irreducible representation. Hope that every representation is a sum of irreducible representations. Of course, this is false. And then very happily make a list of those which are irreducible. So this is the standard yoga in representation theory. And we will see something like that in further lectures when people will talk about Lie groups, like GL2R. But in the realm of p-adic groups, in this realm, it turns out that this question, make a list, which essentially talks about the set here G in this language, is not the most sensible question to ask from the very beginning. This was what people did. Okay, that's kind of I think historically that's the way things happened. OK, so in terms of setup, also in the case of, so if we all know what a representation, so this is a main goal. This is the main goal. And I should say that, for example, the answer to this question is closely related to number theory. So in particular, what I'm referring here is to two-dimensional representations of the Galois group of the absolute Galois group of QP. OK? So this one can think about, this is a number theoretic side, which turned out to be related to this question. I should write here with quotes, because this is not exactly right, but it's close enough that I allow myself to write this on the blackboard. OK, so what I want to do is to put this example in a much larger setup. So let's generalization number 1. Instead of GL2 of QP, we can start with, say, other groups. Yes, why not symplectic group or orthogonal group, or for that matter, some other algebraic groups, which are defined over the field QP. And obviously, the field QP is just one of his kind. So the kind are local fields. So more generally, so slightly more general setup, a more general setup is the following. So F is a local non-Archimedean field. It's complete. So I'm not giving the definition, but you should hold just QP as your favorite example. OK? In fact, these fields are kind of classified. We sort of know them. There are finite extensions of QP if the characteristic is 0, and if it's a positive characteristic field, again, there is some kind of description what it can be. And we take G to be what is called a linear algebraic group defined over the field F. So GL2 is one example. GL3 is another. Okay? And then we form a group, or first of all, a set, the set of F points of this algebraic group. So this set is two things. It's a group, and it turns out that it's more than a group. It's not just a group. In the same way that GL2 of R is not just a set, it is also a topological group, yes, which is a Lie group in the case of real numbers. Here, it turns out that this is a topological group, and we have a name for such groups. So what I'm doing is a two-step generalization. The first is just an example. Then we have a class of examples. And it turns out that all these examples satisfy that there are topological groups which satisfy few properties. So it turns out that it's better to axiomatize this. And this is given the name of an L group. So this sits as a subclass of what people sometimes called, or Bernstein and Zelevinsky called in their paper, L groups. Let me write down the definition. So so maybe before that, before giving the definition, I just want to remind you something about QP, so you will have a little bit more feeling what's going on. Maybe I will just get some feeling about the audience. How many of you know the notion of an L group? Okay, so this is the vast majority. Okay, so reminder, very quick reminder about QP or about this F. So it could be a reminder from previous life. So QP contains in it a certain ring of elements whose absolute value is less than or equal to 1. So it's a definition and a claim. This is a subring. In the case where F is actually equal to QP, wonder about F. So if F is QP, then this ring has a name. It is denoted by ZP. And it is indeed obtained from taking the integers which are contained in Q and completing them with respect to the p-adic valuation. Okay? Okay, so I want to emphasize this. So A less than or equal to 1 and B less than or equal to 1 really implies that A plus B is less than or equal to 1, and I'm on record here. Okay? So this is the main property of the unramified, the non-Archimedean valuation. Yes? This is the non-Archimedean. Okay? In fact, this ring is a local ring. Namely, it contains a unique maximal ideal. This is a prime ideal. And if we consider this collection of A for which A is less than or equal, strictly less than 1, then this is a prime ideal. Okay? So this is a certain structure or object which good to have in mind. Furthermore, if we focus on the group GL2 or GLN, then these structures, and maybe a little bit more, allow us to define interesting subgroups of GL2. So let me right away write down. So if G is equal to GL2 of QP, so one of the properties of ZP, which is easy to check, this ring O, is that it is compact. Okay? And one can easily check or think about that. We will denote by K0 in this setup and in similar ones the group GL2 of ZP, which is here. And this is a compact subgroup. So this is not surprising, but the shocking thing is that it is open. Okay? Okay, so this is just kind of a little bit about the feel of these objects. Now we can write down some abstract definition which means nothing, but of course it sets up the theory. You cannot have a theory without definitions. So let me remind what we want to do. We want to define what kind of groups we want to study, and then to define what kind of representations of these groups we want to study. And then we collect all these objects in a category, and lo and behold, we will have this M of G. That's it. Lectures are done. Okay? At least half of it. Okay. So so the definition, the notion is, I don't know if red is visible. Is red visible? Not really. An L space is, so it's a Hausdorff topological space. I will assume that so it's a locally compact Hausdorff topological space. And so this is, okay, this is a standard object that we study in mathematics, namely locally compact Hausdorff spaces, but such that, so the following property holds. So we want to have a countable basis which consists of open compact subsets. Okay? It admits countable base consisting of open compact subsets. Okay, so I haven't really showed in the example what's going on, so let me elaborate a little bit here. Inside of QP, so there is a technology to cover O with P. So the technology is that we consider the set O mod P. This is a finite set. It's not just a finite set. In fact, it's a field. I told you it's a prime maximal ideal. So this is a field, in fact. It's a finite field. So it has a name. Just have one of your favorite finite fields. But in fact, it means that O has really a covering as tessellations, just some kind of finite cover with tessellations of P, translates of P. Okay? This leads to some interesting picture. So let's draw the unit circle. So this, of course, I never took a spaceship to the p-adic numbers, but okay, let's draw something. So this is some unit circle, and within, so this is O. This is kind of some mental image of O. And so O contains within P. The evaluation is discrete, so it means that there are no elements which sit here somehow. Yes? Every element either is in P or it sits on the shell, on the border. Okay? And in fact, what we see here is that we can cover O, and I should have written that, in a disjoint way using this guy, let's think about whatever, a dime, and some translate which are situated along the circumference. So the picture is a bit deluding. I mean, maybe this is a little bit smaller. So it is something like that, and with its translate, we get some kind of a disjoint covering. Okay? So this is a beginning of how to think about the p-adic numbers and the p-adic field. And in fact, if we think about this in a multiplicative way, then we can come up with the following subgroups of GL2. The subgroups being, I will denote them by Km. They are called the congruent subgroups. Okay? So they consist of matrices, say, in GL2 O. So this means that it's a 2 by 2 matrix. All its elements belong to O. It's an invertible matrix. And I want the matrix to be congruent to the identity matrix if I view it from a microscope that can see only up to the precision degree of p to the m. Okay? So this is easy. It's easy to see that this is a compact open subgroup. So when I say easy to see, it means that it's an exercise you have to do, either on the spot or think about it on the bus or whatever. Don't do that when you are driving, but you have to do it. Otherwise, there is no point in continuing talking about categories. These are completely trivial exercises, which you have to do. So this is a compact open subgroup, and in fact, the collection Km defines the topology of G in the vicinity of the identity. Okay, so you can use these as just a collection of open neighborhoods for the identity. Okay? So this is something you don't have for a group like GL2R. This is a big difference between the groups we are studying and the real groups. Okay, so we have a definition of an L-space. And maybe you ask yourself, so what is an L group? So definition, proposition. An L group is, I'll just give it as a definition, is a group which, let's just say, it's a topological L space which is a group. Okay? And it turns out that this is a topological group, so the action is, in fact, continuous. Okay, let me take it as actually, I will take the strong definition, and I don't want to talk about details like that here. Otherwise, if I will do that, I will not be able to come to things I really want to talk about. So, key fact is the following. So there will be a few key facts. The first key fact is related to L-spaces and where they come from. So how to produce L-spaces. I'm going to give you a machine. So suppose that F is one of our beloved field. So it's a non-Archimedean local field. And X is an algebraic variety. Some people say of finite type. I'm afraid of these notions. Algebraic variety defined over F. So for example, an algebraic variety could be the affine 5 space or the projective 7 space. Okay? These are algebraic varieties. Then X of F is an L space. So what am I saying here? To be more honest, what I'm trying to say is that X of F can be given the structure, can be given a topology. So this is an exercise. It's a fact exercise. For example, if you start with the affine line, A1, and you look at the F points, you get F, and F is a topological space, which satisfies these properties. So you have to explain what is a countable basis which consists of open compact subsets. Okay, that's the reason I was talking about this O and the way that you can shrink it further. This P to the M is kind of a shrinking of that. So in this way, you can describe the topology using compact open subsets. Okay? So again, this is an exercise. By the way, maybe a more interesting exercise is to show that if you took, say, the projective space, you get a compact L space. Okay, this is the standard proof that shows that the projective space is compact. In the real case, for example, we'll give you that as well. Okay, maybe additionally show that PNF is compact. Okay, so this is some fact about L spaces. Let me just check my watch to see how bad it is. Okay. I may have pushed something here. May or may not, I don't know. Okay, sorry. Okay, so I'm sorry. I want to make a correction here. So I hope this is on record. So I want to move this word here. Topological group, which is an L space. I'm sorry. I apologize. Okay. Okay. So so we have this definition, and we have some examples on the blackboard, which I'm going to erase now. And there are some properties of these spaces. I'm not going to give a lot of them. I have given you a source of examples. You start with any algebraic variety. You take the F points. Then you get an L space. So similarly, you can start with an algebraic group. Take the F points. You will get an L group. Okay? Now, what's important is that the way we get representations, where do we get representations from? So we also want to have some mental image of that. The way we get representation is in basically a way that the group acts on a vector space in some reasonable way. So where do we get vector spaces from? The simplest way is to actually have a geometric space on which your group is acting, and then consider functions on this space, and then you get a vector space on which your group acts. Okay, if you don't want functions, you take a sheaf and take sections of that or cohomologies of that, but basically that's what you do. Okay, so the key geometry here would be how L groups act on L spaces. I'm not going to enter that at the moment. Maybe later I will refer to some properties of that. I'm now ready to give a definition. So later we will see some basic properties of actions of L groups on L spaces, and which are relevant for constructing representations. But of course, I can't resist giving you already one example. The basic example that I want to give you is you consider the following subgroup B Well, probably what I'm writing now is not absolutely correct, so let's write this. The following subgroup of GL2F, the letter B is used because it is sometimes called a Borel subgroup. Okay? So this is just a subgroup, the subgroup of upper triangular matrices inside of GL2. Then a nice exercise is to identify the set of the homogeneous space G mod B with the projective line with points in F. So this is an L space, okay? And second is describe an action of G on certain functions on P1 of F. Okay, so this is an example of a representation of the group GL2. It belongs to a big class of representations called sometimes principal series representations. But I just wanted to put it in the box of a group acting on a space, in this case a homogeneous space, which leads to a representation of the group. But an immediate question is asked here, what do you mean here by functions on an L space? Okay? So if we want to really construct representations, we will need to discuss these things. We will need to have some kind of analysis on L spaces. Okay? Okay, so we are now ready for another definition. Well, I'm not so sure we are ready, but I will give it anyway. The definition is that of smooth representation of an L group. Okay? So,
where are these functions taking values?
Okay, so the way I wrote it down, you can do whatever you want. Okay? But I will be interested in this course. I will talk on actions on complex vector spaces. So in particular, I will ask these functions to take values in the complex numbers. Okay? So thank you for the question. So I will consider representations on complex vector spaces. So this is the key notion. It's called smooth representation of an L group G. So in particular, it includes, just terminology which I'm using from time to time. For me, a p-adic group is obtained by taking some algebraic group, linear algebraic group, and considering the f points of that group. So this is a special instant of an L group, instance of an L group, which I'm considered as, I would say, more equal than the other examples. It's more important for me because these are the examples which occur in real life or in applications to number theory. But the theory as such allows the discussion of smooth representation of L groups. Okay? So what is a representation? It's basically very simple. So we sometimes write it as a triple pi VG. Okay, the G we know what it is. It's an L group. Pi is a map from G times V to V. Okay, so do we need to say what V is? No, because, okay, we should. So V is a complex vector space. Okay? And pi is just an action map. So formally, pi GV is something which, if I write it as G dot V, then it satisfies, or denote, and then I require that G1, G2 dot V is G1, G2 dot V, and linearity. Okay? So this is not the end of the definition. This is just saying what a representation means. No. What? Okay, so this is just a representation as you know from the theory of finite groups, for example. Now, we know that in the theory of Lie groups, the requirement is that this action map is continuous. And one can start questioning whether it's continuous in each variable separately or in a strong way or in a weak way. In this case, our condition is the following. Smoothness can actually be translated to continuity, but at the moment I will just write it straight. What?
Is V finite dimensional?
No, just complex vector space. Okay, for example, okay, mostly it will be infinite dimensional. For every v in V, the function which sends G to G times, let's give it a name, F sub Vg. This is the action map. Should be required to be locally constant. Now, this means nothing. We didn't say what locally constant functions are. Nevertheless, it's important for me to write it in this way. We can write it in a more cryptic way, saying that the collection of G in G, for which GV is equal to V. Okay, this object has a name. This is called the stabilizer inside of G of the vector V. Is open. Okay? So what we want is that if some guy preserves V, then a small perturbation of that will also preserve my V. Okay? So another way of saying it, maybe I write it as an exercise. Endow V with the discrete topology then the condition that I have written now spelled out explicitly just means that this map pi is continuous. Okay? then pi v g is smooth if and only if pi is continuous. Pi is continuous. Okay. Okay, so this is the notion we are interested in. And why we are interested in that, maybe at the beginning it's not so clear, maybe this is slightly maybe convincing. The point is that we have a lot of examples which comes from nature, and they satisfy this property. Okay? So given an L group G, we can consider two types of objects. Rep G, this would consist of all complex representations pi GV, and we can consider M of G. Well, I hope that there are no set theorists in the audience. Okay? And MG would be all smooth complex representations pi GV. Okay? So we have described M of G as a subset of rep G. Okay? In fact, it's better to think about this containment as a functor, which is just a forgetful functor. You start with a smooth representation and you forget. It's still a representation. And then you naturally ask yourself whether this functor has an adjoint. And it does. So an adjoint, it means a construction, a canonical way, a functorial way of starting with some representation and forcing it to be smooth. Well, you cannot do that. But maybe you can construct out of it a smooth representation, and such a functor exists. Given a representation V, you can consider the subset of vectors in V, which consist of smooth vectors. V in V, so that Fv is locally constant. If you look upstairs, you would see that the condition is required for every V. So I only pick up those for which it holds, and it is rather easy to show that this is a subvector space which is G invariant, and it affords a smooth representation. So it's an exercise to study, look for yourself, what is the functorial properties of these two functors. They're just adjoint functors, as usual. Yeah?
We didn't say what is morphism yet. So
what?
we didn't define morphisms yet, so when you say adjoint functor, it's not...
You're absolutely right. I never said the word category. I just started with something which is not a set and asked for forgiveness. So yeah, there is a category here. We will soon discuss this object, and we will give it. So this is the object we want to study. So as I said, my goal is to put my hand, to have enough letters to describe this object which I want to talk about. And it is consisting of smooth representations defined above. And this is a category. In fact, maybe I'll write here a theorem. It's not a difficult theorem. I'm not going to prove it, but maybe I will indicate some aspects of it. It's a theorem, but not because it's difficult. It's really a proposition in terms of difficulty, but it's important to know that. M of G is an abelian category with enough projective and injective objects. I will say something about the proof of this result, maybe even about the definition of these notions, but it's good to know. It means that it's good to know in the sense that we are up to something. We have something that we can work with. If you're an algebraist, you know that then you can do some kind of homological algebra, for example. There is a relevant question whether this category has nice finiteness properties. Is it true that every object has a resolution of finite length or of some bounded length? Does it have a cohomological dimension? So these questions become meaningful. Okay, so I haven't written on the blackboard the definition of abelian category. I don't think it's a good idea to talk about that here, but at least it gives us the possibility to talk about sub-objects. Okay? By the way, if you look in the definitions, maybe you want AB1, whatever, in order to have the zero object or whatever, some stupidities like that. But at any rate, immediately we have a notion of irreducible objects. Okay? So I define here G to be the set of equivalence classes, of irreducible objects. Okay, so these are the two objects I wanted to put my hands on. And as I explained, at the moment we have no clue how this category looks like. By the way, maybe I did not emphasize here. There is an exercise here waiting for you. You are asking a good question. I never defined morphisms. But OK, what are morphisms between representations? Standard thing. OK? Now, a fact related to the adjunction there is that if you start from a smooth representation and you move to some representation, then your image is always going to be in the smooth part. Okay? This is some simple exercise on the level of vectors whose content is exactly the adjunction I was alluding to. So just think about that in terms. So this home is taken in the category of all representations, and this is taken in the category M of G. Okay? So in fact, a better way to write it is to erase the SM here and to say that this is for every V in M of G and for every W in rep G, and then actually to write here forget me, and this is your adjunction. Okay. In fact, this is the correct definition of what is the smooth part. Maybe the reason it's lower there and upper there because that's the correct one. This is the stupid definition, and they're the same. Right, just a mistake. Okay, so now somehow I want to quickly indicate how the statement above is being proven, or at least how to put it in a box and send it to somewhere. You see, if you have a ring with a unit, then, so what is the basic example of abelian categories? You start with a unital ring, and you look at modules over that ring. So it would be really neat if M of G is just modules over a certain ring. Okay, now you think about it, you say, of course, it must be true, because we know that if we have a representation of a group, it lifts to a representation of a certain algebra. So take that algebra, and it's a module over that algebra. This would be your ring. So something bad